All right, so let's look at a few more antidifferentiation rules. We've already gone over the constant rule, the constant times a function rule, the polynomial rule, and the power rule for finding an integral. We didn't explicitly go over, but it makes sense that the integral or the antiderivative of 0 equals some constant, because when we take the derivative of a constant, we get 0. So the remaining rules in this section, which are the basic rules, are all trigs. So the answers are just like looking at 0, and just like when we looked at this second one here for the constant rule. We are just able to say for a fact, without any kind of proof or discussion, that the antiderivative of cosine of x equals sine x, because the derivative of sine x, working in the opposite direction, would give us cosine. So we know the antiderivative of all of these trig functions, because if I calculated the derivative of negative cos, I would get sine. The derivative of tan, I'd get secant squared, the derivative of secant x, I'd get secant x tan x, and so on all the way down. And since we know that to be true, then we can say definitively that the opposite is also true. And so we know exactly what the integral or the antiderivative of these trig functions are. So let's do a couple of examples just using the rules. Let's find the antiderivative of sine x plus 3 secant squared x. And of course dx, because we're taking the derivative on the variable x. So let's first break this apart. So we're going to use the rule that I call the polynomial rule, but it could be the parts rule. I'm sure there's some technical name for it. I just don't know it. So let's just go ahead and break this apart into two separate derivatives. So this is going to be the same thing as the antiderivative, into two separate integrals. The antiderivative of sine x plus the did you guys catch that? I made a mistake. Dx plus the antiderivative of 3 secant squared x dx. Well, first, the antiderivative of sine x, we know from here, is negative cos x. So I can lose the symbol because we're finding the antiderivative, negative cos x, and then plus, well, I'm going to have to do two steps because I want to first apply the constant times a function rule. So I get 3 times the antiderivative of secant squared x dx. And now, finally, negative cos x plus 3 times the derivative of secant squared x, the antiderivative of secant squared x is tan x. Plus c. Never, 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 ever forget plus c. There'll come a time where we won't have to use plus c because we'll be dealing with, will take us directly to the actual value, and so we won't have to put that little disclaimer in there that there's a plus c. But in the meantime, you just have to always remember to use plus c. Never, never forget. All right, let's do another example. Let's find the antiderivative of cos cubed t plus 1 over cos squared t. And so, of course, now it's with respect to t, so it's dt in our formula. So to find the antiderivative, first let's kind of clean this up a little bit, because we're sort of dealing with this whole, it looks like we have a denominator with 2 different parts to the numerator. And so just like when we were working with the polynomial, we can rewrite this as cos squared t over cos squared t. That's kind of nice. It's just going to be 1 dt plus the integral or the antiderivative of 1 over cos squared t dt. So let's continue to rewrite this. The first one is super easy, right? We're looking for the antiderivative of 1 dt plus This one, I don't have a rule for a 1 over cos squared of t, but I definitely know that 1 over cos squared of t is actually, using a trig identity, the secant squared of t dt. Now I can totally differentiate. Well, we know that if I'm looking for the antiderivative of the number 1, I'm actually looking for x, or the antiderivative of any constant 1 is just 1 times that constant, or 1 times that variable. So a constant means kx. So in this case, my constant is 1, so 1x, or just x, plus, using my rule, tan x is the antiderivative of secant squared of t. And I've made a mistake here by changing my variables. So this would be t plus tan t, because the antiderivative of secant squared of t is tan t. And then the thing we never forget, because that would be a terrible, terrible sin, is plus c. So the solution for this antiderivative is t plus tan t plus c. All right, so since I have about 11 more minutes, I'm going to just keep doing some more examples. And maybe after I write down the problem, you could turn off the video and challenge yourself to see if you can do it. But whatever you want to do is fine with me. So let's find the antiderivative of the square root of x cubed plus 8 over x to the 4th minus 1 dx. Okay, so let's use, I'm not going to use obviously any trig rules here. First I want to use the polynomial rule, and I'm going to rewrite this as x to the 3/2 dx plus, I'm sorry, the antiderivative of x to the 3/2 dx plus the antiderivative of 8x to the negative 4 dx minus the antiderivative 1 dx. So you'll just say antiderivative dx. All right, so then first one is just use the rule for a power, the power rule for antiderivatives, and that would be x to the 3/2 plus 1 over 3/2 plus 1. And so that gives me 3/2 plus 1 is the same as 1 is the same as 2/2, so 5/2. So I would have 5/2 in the denominator. And in the numerator, I'd have x to the 5/2 plus 8 times the integral of x to the minus 4, but minus 4 in the numerator, x to the minus 4 plus 1 over minus 4 plus 1 means that I have in the numerator x to the negative 3 over negative 4 plus 1, which is negative 3, plus c. So now let's clean this all up. Well, denominator that has a fraction in it just means the reciprocal, multiplied by the reciprocal. So I have 2/5 x to the 5/2. Let's go ahead and write that out as a radical. Since I started with a radical, let's finish up with a radical. Plus, or in this case, minus, because a positive and a negative makes a negative, 8/3 x cubed in the denominator. Just going to bring that negative 3 back down. Plus c. Okay, and now don't shoot me because I got carried away, which I did. I'm sure you caught it. Minus x, right? So minus, if 1 is the leading constant, then this is x. Now plus c minus x plus c. So example 4. Let's find the antiderivative of the square root of t minus t plus t cubed all over the cubed root of t. And of course, we hate this. This is a bunch of ugly numbers to work with, but it's not that it's not going to be hard to work with in all actuality. I think I won't skip any steps, so let's just divide this out into 3 separate antiderivatives. So I have the square root of t, which is just t to the 1/2, divided by t to the 1/3, minus t to the first power divided by t to the 1/3, plus t cubed divided by t to the 1/3, dt, dt, and dt. Okay, another round of simplification. T to the 1/2 minus t to the 1/2 minus 1/3, 1/2 minus 1/3, so that's just 3 minus 2, which is 1/6. So this is the antiderivative of t to the 1/6 dt minus t to the first power minus 1/3 means 3 minus 1 is 2/3, minus the antiderivative of t to the 2/3 dt plus the antiderivative of t cubed minus 1/3, so 9 minus 1 is 8/3. So still not loving the numbers, but totally doable. Now all I have to do is apply my rule. So that's t to the 1/6 plus 1 over 1/6 plus 1. Okay, minus t to the 2/3. Oh, let's write it this way because I'm going to do a little arithmetic on it. 2/3 plus 1 all over 2/3 plus 1 plus t to the 8/3 plus 1 all over 8/3 plus 1. So that is t to the 1/6, so that's 1 plus 6 is 7/6. All over, and I've already done the arithmetic, 7/6 minus t to the 2 plus 3 is 5/3. All over, already did the arithmetic, plus t to the 8/3 plus 1 is 8 plus 3, 11/3, all over 11/3. And now let's finish it all up by getting rid of these fractions in the denominator. So I have 6/7 t to the 7/6 minus 3/5 t to the 5/3 plus 3/11 t to the 11/3 plus c plus c plus c. Don't forget that. Okay, so my final solution here, 6/7 t to the 7/6 all the way over to plus c. And the really kind of sad thing at this stage of the game is that I'm going to tell you that as complicated as it was to work with all these little fractions, these are the easy kinds of antiderivatives to find. Yikes! All right, one more example. I have plenty. All right, our last one then, example 5, is we want to kind of mix it up a little bit. We want to find the derivative. So we're looking for the d dx of the antiderivative of x squared plus 7 over x squared minus 10 dx. Okay, so the first thing we want to do is find the antiderivative of this number, and then once we get that, we're going to take the derivative of the original. Now hopefully you already went, huh? What is she talking about? Why would we take the antiderivative Because the truth is, all we're doing is taking the derivative of an antiderivative, and we know that the antiderivative and the derivative are inverse functions of each other, which means they undo each other, so they just disappear, and the answer actually ends up, well, I don't need this part anymore either. The answer actually ends up being x squared plus 7 over x squared minus 10. A little bit of a trick. Just a little bit of a thought process to remind you that the derivative, or taking the derivative of a function, is the inverse of taking the antiderivative of the derivative of the function. So this wraps up our lesson on antidifferentiation rules, or basic rules for finding the integral of numbers, which is the same as antidifferentiation, although the integral has another more specific meaning that we'll talk about next time.